3-body abrasive wear studies on EN-8 steel by Alumina, Zirconia, fly ash-based thermal coating. Abstract: an investigation was made to evaluate the effect of the incorporation of alumina, zirconia, and in combination with fly ash on the abrasive wear behavior of EN-8 steel. The wear behavior of plain EN-8 steel and different particles like alumina, zirconia, and fly ash coatings studied systematically with respect to load, sliding speed. The wear volume loss increases with increasing load. However, the specific wear rate decreases with thermal coating of alumina, zirconia, and fly ash on EN-8 steel. It is revealed that the better wear resistance of the EN-8 steel by using thermal coating. It is also noted that weight loss increases with increase in load and speed. Meanwhile, the wear mechanisms of EN-8 steel and with different coatings, like Al2O3, ZrO2, fly ash, percentage is described and analyzed. Keywords: 3-body abrasive rubber wheels, alumina, zirconia, EN-8 STEEL, wear mechanism. 1. Introduction. 3-body abrasive wear is defined as wear triggered by free rolling and sliding of particles that are confined by two counter faces experiencing a relative sliding motion. 1. The particles involved in 3-body abrasive wear could be generated by wear debris or have an external source such as sand and soot. The role of lubricant-borne debris and their deformation and fracture on 3-body abrasive wear was investigated in REF 2. 3-body abrasive wear originated from the presence of soot particles in lubricated contacts is a key contributor to wear in diesel engines. 3, 4. Elevated operating temperatures, higher friction, and intensified wear rates in gears as a result of lubricant contamination were also investigated. 5. Razagizari.et al. 6 reported on 3-body abrasive wear of hard coatings. They concluded that ratio of abrasive hardness to bearing surface plays an important role in 3-body abrasive situations. JG Alotibi.et al. 7 studied the wear behavior and wear mechanism of different metals sliding against stainless steel counterface. They concluded that specific wear rate versus sliding distance is almost same for all metals sliding stainless steel. It is divided into two regions, running in and steady state. In the later, the specific wear rate is almost steady with increase in sliding distance. Bocheo Zheng and Haifahang8.et al. studied the 3-body abrasive wear behavior of cementite with different chromium concentrations. They concluded that when Cr content less than 6.03 Wt% single-phase cementite was obtained by Ma and Spa, an increase in Cr led to improved hardness and wear resistance. When Cr content less than 8.22%, Cr atoms are distributed in cementite to form Cr-rich zones of more hardness. These zones reduces the pit department and roughness and improves the cementite abrasive resistance. S. Das Bakshi, P.H. Shipway.et al. 9 reported on the 3-body abrasive wear of fine perlite, nanostruidbanite, and martensite. They concluded that hardest phase martensite has greater wear rate, whereas perlite better resistance abrasion. It also concluded that banite wears by combination of grooving and small minor pitting, whereas in martensite cutting mechanism is dominant. Kai Hung John Yaman Gao 10et.al. studied the 3-body abrasive wear resistance of iron matrix composites reinforced with ceramic particles. They concluded that wear resistance of the composite is mainly related to the fracture strength and bending strength of ceramic particles. The ZTA 55-60 ZrO2 reinforced Cr25 composite exhibit good wear resistance, which 6 times more than that of cast iron matrix. A. Senna and J. Doyle 11et.al. investigated on wear mechanisms in polymer matrix composites abraded by bulk solids. They concluded that the abrasive resistance of reinforced composite material is a micro-mechanisms process that occurs during abrasive wear, which in turn, are strongly depend upon the hardness of wear media. Both 2-body and 3-body wear patterns are possible by bulk solid sliding across polymer matrix composites. Antiiao.et.al. 12 studied on wear resistance and wear mechanism of WC 12% CO thermal sprayed coatings in 3-body abrasion. They concluded that micro-polishing and gradual degradation of the lamellae was predominant wear mechanism in tests with SiO2 abrasives. The wear mechanism with Al2O3 abrasives was plastic deformation. A.P. Harsha.NUS Tiwari 13.Et.Al reported on 3-body abrasive wear behavior of polyaryl ether ketone composites. They concluded that abrasive wear rate is higher in composites than the neat matrix at different loads. 2 experimental details. 2.1 Materials. In this experiment, metal substratate, EN-8, plate of thickness 20 mm, thickness length 5 m, purchased from Surya Steels and Alloys, Pina Industrial Area, Bangalore. The metal substrate is grind with surface grinding machine to obtain surface finish. The coating process is carried out in Spraymit Surface Technology Limited, Pina, Bangalore. Coating materials like alumina, zirconia, fly ash are coated on the metal substrate using plasma spray coating to get the thickness of 150 to 200 microns. 2.2 EN-8 carbon steel grade equivalents. Other steel grades in ASTM, DIN, JIS standards are similar and equivalent to EN-8 steel, as follows. EN-8 steel having low tensile strength, used for general engineering purpose and production of lightly stressed components. The material had properties like good wettability and much inability characteristics and has hard wearing surface. It is process wear molten or heated material on metal substrate to provide a coating. During the process, the powder material is injected to higher temperature plasma flame where it is heated and subjected to high velocity. The higher temperature material impacted on the substrate and cools rapidly, forming strong coating. The plasma spray coating, sometimes also called as cold process, relative to the substrate material being coated, as the subject temperature can be kept lower during the process. 2.3 Abrasive wear test. 3-body tests were conducted as per the ASTM G65 standard conditions for measuring wear loss using rubber wheel test rig as shown in figure. The load applied was 39N, 59N, and 79N, and the time duration of 1, 2 and 3 minutes respectively as per the testing condition requirements. The rubber wheel diameter used is 228 mm. Samples were weighed before and after test using the mass balance of accuracy 0.001 kg and the weight loss is recorded. The schematic diagram used for wear test is shown in figure. 4. 3 Results and discussion. 3.1 Microstructure test results. The microstructure test is conducted by using optical metallurgical microscope. The test method used is 7739 Part V-1976, RA 2007, ASM Metals Handbook Volume 9. The final results conclude that microstructure consists of fine grains of ferrite and perlite. It is in normalized condition. Using scanning electron microscope, SEM, the electrons interact with atoms in the sample, producing various signals that contain information about the surface topography and composition of the sample. For the test specimen, using electron beam is scanned in a raster scan pattern, and the position of the beam is combined with the intensity of the detected signal to produce an image. The Sem analysis is done for different EN-8 steel specimen coated by alumina zirconia fly ash in various range, 10 m, 20 m, 50 m and 100 m. From the test it shows weight and atomic percentage of constituents varies by increasing the nano coating on test specimen. From the SEM investigation observed that plowing mechanism is seen on the worn out surfaces with grooves and voids. For conclusion. It is found that weight loss increases with increase in speed and load before and after coating. But wear performance is improved after coating as compared to before coating. It is also observed that wear performance is improved with lower speed and lower load as compared to higher load and higher speed. From the SEM investigation observed that plowing mechanism is seen on the worn out surfaces with grooves and voids.